Okay, number 35. It says, for the following exercises, use a graphing utility to estimate the local extrema of each function and to estimate the intervals on which the function is increasing and decreasing. So they want you to use your graph around this, and I have, as usual, on my computer printout using my computer. And let's see what we've got here. F of x is, let's see, f of x is x to the fourth minus 4x cubed plus 5. Alright, so in order to graph this so it looks halfway decent, we need to make a table of values to get our viewing window. Alright, so I've come up with a little table here, and what you're going to have to do is substitute these values of x into this function and see what the y values are. And well, let me just draw the table. You can use your own table or you can use mine. So I have two columns, one for x and one for f of x. Or in other words, one for x and one for y, or where y equals f of x. Okay. So if let's start with negative 10, x negative 10. Plug in negative 10 into the formula, so negative 10 to the fourths, and then minus 4 times negative 10 cubed plus 5. Go through that whole process, you'll get 14,005. Alright, negative 5. I'll leave the details of the computation to you. Don't forget order of operations. When you substitute the negative 10, you evaluate the power first, and then you do the multiplying if there is any, and then adding and subtracting last. Okay. So if x is negative 5, y is 1,130. If x is negative 4, y is 517. If x is negative 3, y is 194. If x is negative 2, y is 53. If x is negative 1, y is 10. If x is 0, y is 5. If x is 1, y is 2. If x is 2, y is negative 11. Let's continue over here. X, f of x. We have x3, and y is negative 22. If x is 4, y is 5. If x is 5, y is 130. Starting to go up. If x is 10, y is 6,005. So not being familiar with this function, I used quite a few values of x to get an idea from negative 10 to 10. So what could be a good viewing window for this? Let's say domain. I'll use that as a D. The domain could be from, let's say, negative 2 to 5. Alright, and the range would be from, let's say, negative 25 to 150. Well, let's not say, let's be sure, negative 2. When x is negative 2, y is 53. Alright, and we have some negative values in between there. When x is 5, y is 130. So let's just say from, this is a judgment call, I'm saying from negative 25 to 150. that should cover most of it, because I notice if x is less than -2, it just keeps going up, alright, as you can see here. So you can kind of see the trend. It's going up, up, up as x goes further to the left, and it as you go further to the right, after x equals 5, or let's say x equals 4, you can see it's going up again. Alright. So I think this will pretty much give us an idea of what's going on with this function, and we need to find the local extrema, and estimate the intervals where the function is increasing and decreasing. So, you know, we could keep plugging in values for this, but I can see that we won't need much more than these. Alright, so that's a possible viewing window. You can try something else if you wish. Alright, now here's what I came up with using this as a viewing window. See if I can straighten this out for you. Right, like that. Alright, now if you look carefully at the graph, there's a local minimum right there. When x equals 3, you can evaluate it at x equals 3 and you'll get y equals -22. So that's a local min. We have 3, -22. Alright, now it appears to be flat right in there. Alright, I don't see any max or min there. And so we just have a local min. And what we have is it's increasing as you go to the left here at the very edge, and it's increasing as you go to the right, and it's decreasing there. Okay, so where is it decreasing? It's increasing from right there, x equals 3 to infinity. It's decreasing all the way. See here, it's going down, down, down. It flattens out a bit, but it's still decreasing, and it's going down, down, down. Alright, so when x equals -3, that's where it starts to increase. Alright, so it's decreasing from -infinity to 3. So let me write these down. Increasing from 3 to infinity, and it's decreasing from -infinity to 3. All right. Okay, number 37. 37. We have a square root function here, g of t is equal to t times square root of t plus 3. Now the domain, watch out for the domain of a square root function. You can't have anything negative under the square root, so set t plus 3 greater than or equal to 0 and solve for t. T has to be greater than or equal to -3. Okay, so the domain of this function is oops. Yeah, that's right. Starts at -3 and goes to the right, right? Okay, so -3 to infinity. Positive infinity. Alright. So when we substitute values for t here, it doesn't make sense to go any less than -3 in our table. Alright, so we've got t and g of t. So we'll start at the left endpoint of the domain, -3. So when t is -3, substitute -3 here and here, you get a 0 times -3 is 0. Alright? So when t rather is -2, it turns out to be -2, -1, y is -1.41. Here I'm using decimal equivalents. When t is 0, it's 0, y is 0. When t is 1, y is 2. When t is 2, y is 4.5. When t is 3, y is 7.3. When t is 4, y is 10.6. T is 5, y is 14.1. And when t is 10, y is 36.1. So I'm beginning to see the trend. It's just increasing. Alright. So starts at the, if you look at the graph, if you view this in your mind, it starts at y equals 0 and it goes under the x-axis a little bit, and then it hits the x-axis here again, and then it starts going up, up, up. It's increasing. Alright. So let's give ourselves a viewing window. Let me write my viewing window, instead of using domain and range, because the domain is this, let me write it like this. We've got -3 to 10, let's say, for the t values, -3 to 10. And these are the t values. And that would be, let's see, how far does it go down? Well, -2 here. Let's just say -5 so we don't miss anything. -5 for the y values to, well, if you look at the highest y value here, 36.1, let's just say it's 40 as the high y value. Alright, so you could punch that into your grapher, and here's what I came up with. Okay. All right. So it's obviously has a local min right there. All right. So let me write that down. Local min. Turns out to be at -3. Or rather -2, -2. All right. We already have that in our table. -2, -2. Okay, now what about a local max? Well, the book's answer doesn't include this, but I will tell you that since, if you look here, t equals -3 is an endpoint of the domain, okay? And there is a maximum value locally there. Alright? So, even though the book doesn't have this, since t equals -3 is an endpoint of the domain, this is, excuse me, this is a local max. Alright? So we have a local max at -3, and y value there is 0. Alright. So there you go. So the book, I don't know if your book's corrected that in the copy you have downloaded. The one I downloaded is from summer of 2018, and it doesn't include this local max in the answer. Alright, however, that is a local max, and so that should be there. Alright, and then it's where is it increasing? Well, it's got a low point at the local min at t equals -2, and then it increases. So it increases from -2 to infinity, and it decreases from the end point of its domain at -3, and it goes down to the local min at -2, t equals -2. So from t equals -3, it decreases to -2. Okay, there you go. Okay, number 39. We have a nice big polynomial here. Okay, so we've got m of x is x to the 4th plus 2x cubed minus 12x squared minus 10x plus 4. Now, when you substitute values for x in here, it's kind of a pain to put one value of x in each of these x's, and then, you know, do that on your calculator and figure out what all that equals. All right, so I'm not familiar with the graphing calculators these days, but pardon me while I get my calculator. You've probably never seen these. That's an HP 28S. That's my favorite calculator from way back when I was a student, back in the 80s. All right, a math student, a math major. And with this I can use what's called the solve feature. I can enter this expression into this calculator and press the solve button. If you where's my solve button? Solve, here it is. Right there, solve, S-O-L-V. You press that and it'll pop a screen up that shows x and expression equals. Alright, so you can plug in any value for x, any real number or even a complex number, and it will evaluate this for you. You press expression equals and boom, there's your answer. Alright, it does all the computing for you. Now, this calculator, I don't know if you can see this. This calculator dates back to, where is it? (1986). That's when it was made. Okay. This is back when Hewlett-Packard made calculators appealing to engineering types. But HP has kind of changed their direction. But anyway, now I guess TIs are the reigning kings. But you know, I would think that if my calculator could do this in '86, yours should be able to. So to save yourself all of this computational trouble, that could take quite a while, I would see if your calculator has a feature where you enter this whole thing into the calculator, and somewhere in some menu, you can plug in one value for x, and the calculator will plug it into the function and evaluate it at that value for you. All right, and that'll save you a lot of time, a lot of frustration. You know, you can make mistakes when you do this, when you're tired, and there's a big string of numbers and letters here. So it's well worth the effort to learn it that way. Get out your user's manual and start looking. All right, that's what I had to do. I learned how to use this calculator as problems arose, and I didn't know how to deal with them. So I wondered if there was a shortcut using my calculator, and lo and behold, there usually was. You know, I just had to look in the manual. So of course nowadays manuals are PDF files, but anyway. Try that. See if you can come up with something. Maybe your calculator will do that for you. So that's what I did to evaluate this function. And I used my old 1986 HP 28S. All right. By the way, you can still get those on eBay for a pretty low price. HP 28S's, yeah. Take a look on eBay. The predecessor to the 28S is the 28C, which I also had, but it doesn't have as much memory as the 28S. You know, and back then, those things didn't have much memory at all. So I would get the 28S if you have a choice. All right, if you're into that kind of thing. Okay. Ancient technology, right? All right. We have x and m of x, or xy. If y equals m of x. So if x is negative 10, y is 6,904. If x is negative 5, y is 129. If x is negative 4, y is negative 20. If x is negative 3, y is negative 47. If x is negative 2, y is negative 24. If x is negative 1, y is 1. If x is 0, nice and easy, that's 4. Y is 4. If x is 1, y is negative 15. If x is 2, y is negative 32. If x is 3, y is 1. If x is 4, y is 156. If x is 5, y is 529. One more. If x is 10, y is 10,704. So, all right. Looks like it's increasing as you go to the left on the x-axis, and then when you get near the origin it begins to decrease. It goes, well, it's decreasing, that is, from the left going toward the origin, as you can see in this table. Looks like it starts increasing around at x equals negative 2. So we're going from negative 47 to negative 24. And then it starts to increase a little bit, and then it starts to decrease. Oh, look at that. And then it starts to increase. Okay, so we've got all kinds of stuff going on. So here's a viewing window we could use. Let's say from when x is negative 5 to positive 4. That covers pretty much all the changes. We don't have to go any further than we need to. Negative 5 to 4, so this would be your x values. And, excuse me, from negative, well, let's see, what do we have here? Negative values, the lowest I see is negative 47. That doesn't mean it doesn't go lower than that, but let's say negative 50 as the least y value. And what's the, let's see, if x is negative 4, we get 156. And up here we get 129, so let's say 170. That should get the whole graph in there. So these are the y values. Alright, so I put that viewing window in my computer. And here's what it looks like. Okay, so now my answers, I'll tell you right now, my answers deviate a little from the book's answers. Alright, now again, I evaluated this function using my solve feature on my HP 28S. Alright, and so it was very easy for me to compute these results, and I have rounded some of these answers because they weren't totally exact, but I'm going to stick by my answers over the books. I believe that my answers are correct, and some of the book's answers are not quite correct. Okay, so I'll tell you what I'm talking about here in a minute. Now there's two local mins, if you see here on the graph, here and here. Alright, so turns out local mins we've got x is negative 3.2, y is negative 48. Your book has negative 3.25 and negative 47. Well, you can see my answer is more of a minimum than the book's answer there. Alright, so, and if you don't believe it, plug that in to this function and calculate it, and you get that rounded off. Okay, so if you plug the same thing into, if you plug in their answer, the book's answer, negative 3.25, you won't get something as low as this, even before you round off. Okay, so check that yourself if you don't believe it. And also 2 and negative 32. So those are your two local mins. Alright, the book's got 2.1 negative 32, which isn't quite correct. Alright, this one is the better of the two answers. Alright, trust me, I've checked these, I've double checked. Anytime I disagree with a book, when I write my lesson notes, I always use lesson notes. I always prepare for this beforehand. You know, before I start filming this, I go through the book and I do it myself, and then I look at what I got and compare it to the book's answer, and if I get it wrong or if I don't agree, I double check my work to make sure I did it correctly. And in this case, I think the book's incorrect. Okay, so I'll put it in red notation on my notes so I can let you know, hey, I disagree with the book here. Alright, the local max. Well, that's right near the origin. See, the local max is right there. It's kind of hard for me to move my fingers because it's going opposite of the way I think it's going here. Alright, right there, huh? So local max turns out to be negative 0.4, negative 0.4, and 6. Okay, now your book's got negative 0.56. Okay, again, my answer is the better version, and it is correct. Okay. Alright, and it's increasing. Where is it increasing? Let's get a general overview of where it's increasing. Okay, if you look at the, here it's decreasing down to the min, then it's increasing, and now it starts decreasing, and then it starts increasing. So it's decreasing to the local min on the left, and then it increases to the local max, and then it decreases again to the other local min, and then after that it increases. Alright, so The interval where it's increasing would be negative 3.2 to negative 0.4 union 2 to infinity. Now, the book had different answers for the local mins and local max, so they used their results for these intervals, okay? So again, I'm telling you, I think my version's better, all right? And then it's decreasing from negative infinity to negative 3.2 union negative 0.4 to 2. All right, so there you go. Again, if you have any doubts, double check my work and try the book's answers and see the results. See if you, for example, for this local max, see if you get something better with my answer or the book's answer. Use your calculator, you know, go through the trouble and do all the computation and prove it to yourself, okay? There you go. Okay, we have number 41. They give us a graph. I'll refer you to your book. That's figure 18 in your book. Here's the graph. They don't specify what function this is, but there you go. Okay. Now it says, based on the calculator screenshot, the point 1.333, 5.185, which happens to be that local maximum there, rather, local maximum right there, where the two arrows meet, is which of the following? A relative, that's another name for local maximum of the function. Well, it certainly is that, isn't it? Certainly is that. That is a relative or a local max right there. Okay. Well, it's definitely A, but let's see what the other answers are. B, the vertex of the function. No, there's no vertex for this function. Now, parabolas have vertexes or vertices. All right, that's the low or the high point of the parabola. Triangles have vertices. Okay, that would be the sharp points on a triangle. All right, but there's no vertex here. Okay. C, the absolute maximum? No. Because as you can see from the picture, at least it looks like the function keeps going. And keeps going up, up, up. Where is that? I can't. Here we go. Right there. Keeps going up, up, up. All right. So that point that they're mentioning definitely is not the absolute max, although it is a local or a relative max. D, it's a 0? No, it's not a 0, or another word for that would be root. It's not a root or a 0, because the 0 occurs where it touches the x-axis. In other words, right there. That's the 0, whatever that is, okay? That's the 0 of the function right there. That's where y equals 0, okay? And whatever x value that is, that would be it. So there you go. Okay, number 43. We have f of x equals 1 over x. Find the number b such that the average rate of change of f on the interval from 2 to b is negative 1/10. How do we do this? Well, it's an average rate of change, right? And they give us an interval, 2 to b. So we've got f of x is 1 over x. And the interval's from 2 to b, 2 to b. We want to figure out what b is so that the average rate of change on this interval equals -1/10. All right. So set up your average rate of change formula here. F of b minus f of 2. What's b? I don't know. We're going to figure it out. All right. F of b minus f of 2. But first we need something to set up here to solve. And then b minus 2 below. And set that equal to -1/10. Now, so that's saying the average rate of change of the function f from 2 to b, which is this part here, will equal -1/10. All right, that's the conditions they gave us. All right. Once we plug these values into f of x, we can solve it for b. All right. So what's f of b? It's 1 over b. And what's f of 2? So you subtract f of 2, that's 1 over 2. Over b minus 2 equals -1/10. All right. So we can multiply both sides by b minus 2. Let me do that. Multiply both sides by b minus 2. So we're going to have 1 over b minus 1/2 over b minus 2 times b minus 2. I'm putting that in parentheses because you're multiplying by that whole quantity, equals -1/10 times b minus 2. Multiply both sides by b minus 2. And that'll cancel these out. Alright. Okay. And then we can deal with this part. 1 over b minus 1/2. Well, what's the common denominator? That would be 2b, right? So I need a 2 down here, so I multiply that by 1, but I choose 1 to be 2 over 2. Multiply by 1 so you don't change the value of the fraction. But now we're going to get a common denominator. And then minus 1/2. Now I need a b under there, so I multiply by b over b. Again, that equals 1. But I am getting the common denominator that way. That equals, you can distribute the -1/10 through, but on this one it turns out to be advantageous to leave it like this, -1/10 times b minus 2. You could distribute that again, but it's okay to leave it this way for now because it'll be easier to deal with. So now what we have is 2 over 2b minus b over 2b. So that's 2 minus b over 2b. They both have common denominator, so we can just subtract the numerator. 2 minus b over 2b equals -1/10 times b minus 2. Alright. So if you multiply or you factor out, notice what I have here. A 2 minus b and a -1/10 b minus 2. This is almost 2 minus b, isn't it? This is the negative of that. If you multiply this by negative, you're going to get -b plus 2, or 2 minus b, same as this, right? So I can take that negative sign and distribute it through here. Let me do that. So I think I'll do it here, and then I'll start another line. 2 minus b over 2b equals +1/10, and I'm going to distribute the negative through there. So you get -b plus 2, or 2 minus b. Okay, like that. So Now you don't have to do it exactly how I did it, but the way I'm doing this is kind of a what I think is a cool way to do it. All right. Now you can factor the 1 over 2b here, right? You can think of that as 1 over 2b times 2 minus b. That equals this, right? So you can think of factoring the 1 over 2b out like that. So you're going to have this times 2 minus b equals this times 2 minus b. You see what I'm getting at here? Okay, so you got 1 over 2b times 2 minus b equals 1/10 times 2 minus b. Alright? Therefore, we have a fraction times 2 minus b equals a fraction times 2 minus b. So this times the same thing, well, this must equal this, right? These two fractions must be equal. Alright? Because these are equal, these two factors here, 2 minus b, are equal. So since this is an equation, that means the denominator, well, the numerators are the same, right? 1 and 1. So that means the denominators must also be the same. They must be equal. So you set 2b equal to 10. I put therefore, and that would be 3 dots in a triangular pattern. That means therefore in symbolic logic. Okay, you can, if you use that with your math instructor, they probably will appreciate you for that. All right, they'll say, "Wow, this guy's got some brains," or "This girl's got some brains." All right, so symbolic logic uses that for therefore. 2b equals 10. Solve for b. b equals 5. b equals 5. All right. So again, you could solve it the conventional way. I just kind of, you know, when you've solved things conventionally for many years, you kind of get bored and you want to try something different. Well, this is a little more sophisticated way of doing it, all right? But it does teach you or give you some mathematical insights which you may not have had before, all right? So I decided to show you this way. If you want the conventional way of doing it, you can ask your instructor to show you how to do this conventionally, all right? But you can't always do it this way. It doesn't always work out this way, okay? But when it does, it's pretty nice. Okay, number 45. A driver of a car stopped at a gas station to fill up his gas tank. He looked at his watch and the time read exactly 3:40 p.m. At this time he started pumping gas into the tank. At exactly 3:44, which is 4 minutes later, the tank was full and he noticed that he had pumped 10.7 gallons. So 4 minutes later, he has 10.7 gallons. What's the average rate of flow of the gasoline into the gas tank? And that would be, apparently here we're talking about gallons in minutes, so gallons per minute. What's the average rate of flow? Gallons per minute. Okay, so this is pretty easy to set up. Average rate of flow is equal to, so he had how many gallons? 10.7. And how long? How many minutes? 4 minutes. Basically we're done. 10.7 over 4 gallons per minute. But let's get something more useful. You can plug that into your calculator and that turns out to equal 2.675. Exactly. Gallons per minute. So 10.7 divided by 4 is 2.675. Okay. So there you go. But the books got it rounded off to 2.7 gallons per minute. Okay. Well, this is not that big of a decimal, so I'd say leave it as is. But that definitely rounds off to 2.7. So, Alright, it's your choice, but you know, this is your exact answer if you want it. There you go. Okay, number, the last one, yes, number 47. They give us a graph, figure 19. The graph below illustrates the decay of a radioactive substance over T days. And what I did was, well, it says use the graph to estimate the average decay rate from T equals 5 to T equals 15. So I marked off where it said T equals 5 and T equals 15 on the graph. And I found the Y values using a straight edge on this graph. Of course, I had to print it out to do that. You might have to do that too, because I don't see how you're going to do that on your screen, but here's what I got when I printed it out and used my straight edge. If you can take a look. Alright, you see how I did that? At T equals 5, I drew a vertical line up to the graph, and then I looked at the Y value, or the A value, that's 12. And then I went to 15, drew a vertical line, and then a horizontal line to the Y, or the A axis this time. It's about 6, isn't it? So these are your 2 points that are going to go in your average rate of change, all right, formula. Okay, so it says the average decay rate equals, okay, now we don't have a function here. Apparently it's a function capital A, but we've got to have A of x2, in this case it's T2, A of T2 minus A of T1 over T2 minus T1. Well, let's see. We've got 5 and 12 and 15 and 6, right? Okay, so let me write those down. 5, 12, those are your 2 points that you're concerned with, and 15 and 6, alright? So what are the Y values here? We've got 12 milligrams, these are in milligrams, minus 6 milligrams. 12 minus 6. And we've got days. We've got 5 minus 15. Alright. So this is 6 milligrams over negative 10 days. And that's equal to negative 0.6 milligrams per day. Alright. It's a negative. The average rate of change is negative because from left to right the graph is decreasing. So it's going down from left to right. So that's a negative rate of change. Alright. It's like when you're talking about lines, negative slope, okay, only this isn't a straight line. So this is a negative average, it's a decay rate. You expect it to be negative because when it decays, of course, it gets less and less over time. Well, there you go, guys and gals. It is, and any aliens listening to this in the Zeta Reticuli system, if you're picking up this signal, hello from Earth. Alright? You gotta pardon me, I'm a long-time sci-fi guy. But anyway, that's it, guys and gals. This is the last one in this section. Cool, yay. Good job. That's a thumbs up. Pat yourself on the back. Go get yourself some coffee. put your feet up, watch a little TV, whatever it is you do to relax. And I will see you later in the next section. All right? So have a good one while we're gone. Take care. Bye-bye.